Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss about the module Phase Locked Loop PLL from the paper Electronics. So students, let us see what we are going to learn in this module. First, detailed explanation of PLL with each component will be discussed. Second, we will discuss about the IC PLL 565. Third, phase detector, that is XOR phase detector and edge triggered, will be discussed in this module. Lastly, detailed explanation of voltage controlled oscillator will be discussed in this module. So students, let us start with a basic introduction about the module. The phase locked loop or PLL is a particularly flexible circuit building block. The phase-locked loop PLL can be used for a variety of radio frequency applications, from frequency synthesizers to clock recovery and FM demodulation. As a result, PLL is found in many items of radio frequency equipment, including radio receivers, test equipment, and other items of radio frequency electronics. The PLL was not used in early radio equipments because of the number of different stages required. However, with the advent of radio frequency integrated circuits, the idea of PLL became viable. So initially, relatively low frequency PLLs become available, but as RFIC technology improved, so the frequency at which PLLs would operate rose and high frequency versions become available. PLLs are used in a large variety of applications within radio frequency technology. PLLs can be used as FM demodulator, and they also forms the basis of indirect frequency synthesizers. In addition to this, they can be used for a number of applications, including the regeneration of chopped signals, such as the color burst signal or an analog color television signal, for types of variable frequency filters, and a host of other specialist applications. Locked loop, that is PLL. So a phase locked loop or phase locked loop PLL basically is a control system that generates an output signal whose phase is related to the phase of an input signal. So they are used in communication systems, airborne navigational systems, FM communication, sys computers, etc. So students, let us first discuss about the block diagram of PLL. So the schematically block diagram of PLL is shown in this figure, which consists of phase detector, low pass filter, an error amplifier, and a voltage controlled oscillator or VCO. So if an input signal Vs of frequency Fs is applied to the PLL, the phase detector compares the phase and the frequency of the incoming signal to that of the output VO of the VCO. So if the two signals differ in frequency or in phase, an error voltage VE is generated. So the phase detector is basically a multiplier and produces a sum Fs plus F0 and a difference Fs minus F0 components at its output. The high frequency component Fs plus F0 is removed by the low pass filter, and the difference frequency component is amplified and then applied as control voltage, that is Vc, to the VCO. So the signal Vc shifts the VCO frequency in a direction to reduce the frequency difference between Fs and F0. Once this action starts, we say that the signal is in the capture range. So the VCO continues to change the frequency till the output frequency is exactly the same as the input signal frequency. The circuit is then set to be logged. Once logged, the output frequency F0 of VCO is identical to Fs except for a finite phase difference phi. So this phase difference generates a collective control voltage Vc to shift the VCO frequency from F0 to Fs and thereby maintains the lock. Once locked, PLL tracks the frequency changes of the input signal. So PLL consists of three stages. First, the free running, second, capture, third, logged or tracking. So this figure shows the transient of the low pass filter output versus the capture transient. It can be seen from this figure that as the capture starts, a sine wave, basically a small sine wave, appears due to the difference in the frequency between the VCO and the input signal. So the DC component of the beat drives the VCO towards the lock. So each successive cycle causes the VCO to move closer to the input signal frequency. So the difference in frequency becomes smaller and a large DC component is passed by the filter, shifting the VCO frequency further continues until the VCO locks onto the signal and the difference frequency is DC. So the low pass filter controls the capture range. If VCO frequency is far away, the beat frequency will be too high to pass through the filter and the PLL will not respond. Signal is out of capture band. However, once locked, the filter no longer restricts the PLL. The VCO can track the signal well beyond the capture band. Thus, tracking range is always larger than the capture range. So students, let us now discuss about the lock-in range. Once the PLL is locked, it can track frequency changes in the incoming signals. So the range of frequencies over which the PLL can maintain the lock with the incoming signal is called as the lock-in range or tracking range. The lock range is usually expressed as the percentage of F0, the VCO input frequency. Let us now discuss about the capture range, the range of frequencies over which the PLL can acquire a lock with an input signal is called as a capture range. This parameter is also expressed as the percentage of F0. Let us now discuss about the PLL IC 565. The operating frequency range for this IC is 0.001 to 500 Hz. Operating voltage range is plus minus 6 volts to plus minus 12 volts. Input level is 10 millivolt RMS minimum to 3 volt peak to peak maximum. Input impedance is 10 kilo ohm typically. Output sink current is 1 milliampere typically. Drift in VCO center frequency with temperature is 300 ppm per degree Celsius, and drift in VCO center frequency is 1.5% per supply voltage. So the pinout diagram for this 14-pin 565 IC is shown over here. A value between 2 kilo ohm and 20 kilo ohm is recommended for RT. The VCO running frequency is adjusted with RT and CT to be at the center of the input frequency range. So a short circuit between the pin 4 and pin 5 connects the VCO output to the phase comparator in order to compare F0 with input signal Fs. Phase detectors. There are two types of phase detectors, digital and analog. A phase detector is a comparator which produces a DC output proportional to the difference of voltage available at the input. This may be written as Vp equal to Kp multiplied by phi1 minus phi2, where Vp is the output voltage, phi1 and phi2 these are the phase of the input signals, and we can represent it by phi I1 and phi I2. Kp is the phase detector gain in voltage per radian. So since voltages are both periodic, so finally we can say that output DC level depends on difference of phases. Now when two input frequencies do not match them, phase difference does not remain constant, and so the DC output of phase detector also fluctuates. But when the input frequency matches, then whatever the phase difference is there, it remains constant, and so phase detector output is perfectly stable DC. Thus, when the two frequencies do not match, then phase detector gives a periodic output at different frequencies. Exclusive or phase detector. So this is the schematic for the output from XOR or exclusive OR phase detector. It is obtained as a CMOS IC of type 4070. Both frequencies are provided as input to the XOR phase detector. The XOR output becomes high only if either of the inputs, that is U1 and U2 as shown over here, becomes high. Consider a waveform where input frequency leads the output frequency by theta degrees, that is U1 and U2 has a phase difference of theta degrees. The DC output voltage UD of the comparator will be a function of the phase difference between its two inputs. So output DC voltage is maximum when phase detector is 180 degree because the output of the gate remains high throughout. Let us now discuss about the edge triggered phase detector. Now here the circuit is the RS flip-flop made by NOR gates CD4001. The output of RS flip-flop changes its state on the leading edge of Fs and F0. This detector has a better capture, tracking and locking characteristics as DC output voltage is linear over 360 degree compared to 180 degree of XOR detector, which is schematically shown in this figure. Voltage controlled oscillator. This is the main component of PLL, which is nothing but a free running multi-vibrator and operates at a set frequency F0 called as the free running frequency. This frequency is determined by an external timing capacitor and a resistor. It can also be shifted to either side by applying a DC control voltage Vc to appropriate terminal of the IC. The frequency deviation is directly proportional to the DC voltage and hence it is called as a VCO. So a common type of available VCO in IC form is any SE566. A timing capacitor CT is linearly charged or discharged by a constant current source sink. So the amount of current which can be controlled by changing the voltage Vc applied to the modulating input pin 5 or by changing the timing resistor RT external to IC chip. So the voltage at pin 6 is held at the same voltage as pin 5. Thus, if the modulating voltage at pin 5 is increased, the voltage at pin 6 also increases, resulting in less voltage across RT and thereby decreasing the charging current. So this figure shows the pinout diagram of any SE566 and the typical connection to be used as a voltage controlled oscillator. Students, let us discuss the internal circuit of IC566, which consists of the two components, that is buffer and Schmidt trigger. Schmidt trigger is used for wave shaping circuits. It can be used for generating a square waveform from a sine wave input. Basically, the circuit has two opposite operating states like in all other multi-vibrator circuits. However, the trigger signal is not typically a pulse waveform but a slowly varying AC voltage. Schmidt trigger is level sensitive and switches the output state at two distinct trigger levels. One of the triggering level is called as a lower trigger level LTL and the other as upper trigger level UTL. If we slowly increase the input voltage, we eventually reaches a point where it is slightly more positive than UTP. So when this happens, the error voltage changes the polarity, driving the op-amp into negative saturation. So with the output now negative, the voltage divided feeds back a negative voltage to the non-inverting input, which is referred as the lower trip point LTP, and UTP is the upper trip point. So the output remains in negative saturation as long as the input voltage is more negative than the LTP. So the only way to change the output is to decrease the input voltage until it is slightly more negative than LTP. Then the error voltage changes the polarity and the output switches back to positive saturation. Students, let us now discuss about the buffer. A digital buffer is a special electronic circuit that is used to isolate the input from the output, preventing the impedance of one circuit from altering the impedance of another. The output drive capability is generally much higher than their input signal requirements, and it is used to drive high current loads. For a voltage controlled oscillator generating a sawtooth waveform, the main component is the capacitor, whose charging and discharging actually decides the formation of the output waveform. The input is given in the form of voltage, which can be controlled. This voltage is converted to a current signal and is applied to the capacitor. So as the current passes through the capacitor, it starts charging and a voltage starts building across it. As the capacitor charges and the voltage across it increases gradually, the voltage is compared with the reference voltage using a comparator. When the capacitor voltage exceeds the reference voltage, the comparator generates a high logic output which triggers the transistor, and the capacitor is connected to ground and starts discharging. Thus, the output waveform generated is the representation of the charging and discharging of the capacitor, and the frequency is controlled by the input DC voltage. Let us now discuss about the working of VCO IC566. A small capacitor of 0.001 microfarad should be connected between pin 5 and pin 6 to eliminate the possible oscillations. So the voltage across the capacitor CT is applied to the inverting input terminal of Schmidt Trigger A2 via the buffer amplifier A1. The output voltage swing of the Schmidt Trigger is designed to VCC and 0.5 volts. If RA is equal to RB in the positive feedback loop, the voltage at the non-inverting input terminal of A2 swings from 0.5 VCC to 0.25 VCC. When the voltage at the capacitor CT exceeds 0.5 VCC during charging, the output of the Schmidt trigger go low, that is 0.5 VCC, and the capacitor now discharges, and when it is at 0.25 VCC, the output of the Schmidt trigger goes high. Since the source and sink currents are equal, capacitor charges and discharges for the same amount of time. So this gives a triangular voltage waveform across CT, which is also available at pin 4. The square wave output of the Schmidt trigger is inverted by the inverter A3 and is available at pin 3. The inverter A3 is basically a current amplifier used to drive the load. Let us now discuss about the output frequency of VCO. The total voltage on the capacitor changes from 0.25 VCC to 0.5 VCC as shown in this figure. Thus, delta V is equal to 0.25 VCC. The capacitor charges with a constant current source. So, delta V by delta T equal to I by CT, which implies 0.25 VCC divided by delta T equal to I by CT. So, calculating delta T, we have it is equal to 0.25 VCC CT by I. So, the time period T of the triangular waveform is 2 delta T and the frequency of the oscillator F0 is F0 equal to 1 by T equal to 1 by 2 delta T equal to I by 0.5 VCC CT. But we know that if we calculate the expression for I, which is equal to VCC minus VC divided by CT RT VCC, where VC is the voltage at pin 5. Therefore, F0 is equal to 2 multiplied by VCC minus VC divided by CT RT VCC. Now, there is another parameter, that is voltage to frequency conversion factor kV, which is delta F0 by delta VC. Here delta VC is the modulation voltage required to produce the frequency shift of delta F0 for a VCO. So if F0 is the initial frequency and F1 is the new frequency, then delta F0 is F1 minus F0, which is equal to 2 multiplied by bracket VCC minus VC plus delta VC bracket close by CT RT VCC minus 2 bracket VCC minus VC bracket close divided by CT RT VCC. So after simplification, this is equal to 2 delta VC by CT RT VCC. Now simplifying the expression for delta VC, we get delta F0 CT RT VCC by 2. So if the modulating signal at pin 5 is biased at 7 by 8 VCC, then the VCO output frequency is F0 equal to 2 multiplied by VCC minus 7 by 8 VCC divided by CT RT VCC. This is equal to 1 by 4 CT RT equal to 0.25 divided by CT RT. So the conversion factor becomes kV equal to delta F0 by delta VC equal to 8 F0 by VCC. Low pass filter. The phase detector produces a sum Fs plus F0 and difference Fs minus F0 components at its output. So the high frequency component Fs plus F0 is removed by the low pass filter. The low pass filter not only removes the high frequency components and noise, but also in the dynamic characteristics of the PLL. These characteristics include capture and range, bandwidth and transient response. So if filter bandwidth is reduced, the response increases. However, reducing the bandwidth of the filter also reduces the capture range of the PLL. So the charge on the filter capacitor gives a short time memory to the PLL. Thus, even if the signal becomes less than the noise for a few cycles, the DC voltage on the capacitor continues to shift the frequency of VCO till it picks up the signal again. This produces a high noise impunity and locking ability. So these two figures shows the schematic of the low pass filter, and the second one shows a low pass filter using op-amp. So students, let us summarize what we have learned in this module. First, detailed explanation of PLL having each component which was explained in detail was provided. Second, we discussed about the IC PLL 565. Third, the two types of phase detector, that is exclusive OR phase detector and edge triggered, were discussed. Lastly, that is fourth, we discussed about the detailed explanation of voltage controlled oscillator. Thank you.